Please make sure you have your copy of Which is the Better Antacid. What we'll do is look at how to do the calculations for all the parts of the experiment. Before doing this, you should have watched the video showing how the procedures were followed, and then the video that shows how the data were collected. Now what we'll look at is all the different calculations that go along with the lab. Now just to review, what we're trying to do is we're trying to find out which of these two different antacids, Tums or Gaviscon, is better. Both of them do the same thing. They react with hydrochloric acid in your stomach, but they use different active ingredients to do it. The Tums has one active ingredient, calcium carbonate. It has 1/2 gram. However, the Gaviscon has two active ingredients, aluminum hydroxide and magnesium carbonate. So maybe two ingredients is better than one. But when you look at the mass of those ingredients, it adds to less than the mass of the calcium carbonate in Tums. So maybe Gaviscon having two ingredients isn't as good as calcium carbonate's one. But hold on, let's look at the stoichiometry. The hydrochloric acid that the Tums reacts with, Tums can react with two hydrochloric acid molecules, but one of the ingredients that's in the Gaviscon can react with 3 of them. The other one can react with 2, just like the Tums. Maybe 3 is better than 2, so there's other things to consider as well. But let's look at the price. Tums, each one costs 3 cents. Gaviscon is 4 times more expensive. It costs 12 cents each tablet. So if it costs 4 times more, do you get 4 times the strength, the acid reduction strength? That's what we're trying to find out in our experiment. Which one of these two can use up more hydrochloric acid in a sample of stomach acid? Okay, so what we're going to do is we're going to predict first how much acid each one should use up if the reactions go according to the active ingredient label, and if they are 100% effective according to the stoichiometry calculations. So we'll start by looking at how many grams of hydrochloric acid will react with the 0.500 grams of calcium carbonate that are in Tums. So the thing that we know how many grams of calcium carbonate there are. We're given the number, so that means that calcium carbonate is our X, the thing that we're going to start with. The thing that we're trying to find out, look for the keywords how much or how many. It says that hydrochloric acid is what we're trying to find out. That's why we're doing the calculation. So let's find out the molar mass of that hydrochloric acid. To do that, list the elements, hydrogen and chlorine, count their atoms, one of each, use your periodic table to find their mass, round to the nearest whole number. Hydrogen is 1, and chlorine is 35. So 1 atomic mass unit and 35 atomic mass units. Multiply and add. So 1 mole of hydrochloric acid particles, or molecules, is 36 grams. This is how we count things in chemistry, by using their mass. Now let's find the molar mass of the calcium carbonate. The formula, listing the elements, calcium, carbon, and oxygen, and counting them, 1, 1, and 3. Use your periodic table to find the mass. Calcium is 40, and carbon is 12, and oxygen is 16, rounding to the nearest whole number. So 40 units, 12 units, 16 units. Multiply, add. 100 grams is the mass of 1 mole of calcium carbonate units. So if you had a mole of them, 602 billion trillion, it would weigh 100 grams. That's how we count them, by weighing them. To do the stoichiometry, let's look for those substances in the balanced reaction equation. The calcium carbonate, the thing that we know, our X, and the hydrochloric acid, the thing that we're trying to find out about, the Y. What we need to know is, what is the coefficient? How many of each are in the balanced reaction equation? There are 2 hydrochloric acids for every, there's no number there, that means there's 1, the formula counts itself. For every 1 calcium carbonate, it can react with 2 hydrochloric acid molecules. Alright, now let's put it all together. Starting with what we know, there are 0.500 grams of calcium carbonate in a Tums times 1 mole of calcium carbonate over the molar mass of calcium carbonate, which we calculated, 100 grams of calcium carbonate, times how many moles of our Y substance? Our Y substance is hydrochloric acid. The coefficient is 2, so 2 moles of hydrochloric acid. And on the bottom, how many moles of our X substance? 1 mole of calcium carbonate. Okay. And then on to the last step, the molar mass of our Y substance. Our Y substance, hydrochloric acid. That's why we're doing the problem, to find hydrochloric acid. So 36 grams of hydrochloric acid over 1 mole of hydrochloric acid. See how I was setting this up? I was using the solving strategy up above. Everywhere that there was an X, I put calcium carbonate because that's the thing that we were given to start with. And everywhere there's a Y, I put the hydrochloric acid because that's the thing we're trying to find out about. When we set up the problem, we're setting it up so that units cancel. Grams of calcium carbonate are on the top and bottom of a fraction. Anything divided by itself reduces to 1 and factors out. So I can also cancel out moles of calcium carbonate, moles of hydrochloric acid, and the unit that I'm left with is the one I'm trying to find. How many grams of acid can the calcium carbonate in Tums react with? So, do the math. Multiply across the top. If you multiply those 4 numbers together, you get 36. If you multiply these 3 numbers together, you get 100. And then if you divide the top by the bottom, you get 0.36 grams of hydrochloric acid. 1 Tums uses up 0.36 grams of hydrochloric acid. Now in the analysis that we're doing, I set it up so that each 100 milliliters of stomach acid has 1 tablet dissolved in it. But we're only going to analyze a 20 milliliter sample. So that's 1/5 of a Tums that's going to be actually analyzed. So we're going to divide this by 5 because the sample that we're testing is only 1/5 of a Tums worth of chemistry. So if you divide that 0.36 by 5, you get 0.072 grams of hydrochloric acid. So the samples that we're going to test, we're expecting that the amount of hydrochloric acid that could be used up is this many grams. Let's do the same calculation for the Gaviscon and see what we expect it to be able to do. Okay, so in this problem, we're still trying to find out how many grams of hydrochloric acid can be used up. So that's what we're trying to find out. It's why we're doing the problem. But this time we're going to have 2 different X's. We're going to calculate once for the aluminum hydroxide and once for the magnesium carbonate, both of the ingredients found in the Gaviscon. And then we'll add together the results because both ingredients are working together to reduce the hydrochloric acid in your stomach. Alright, so let's calculate the masses of those. The aluminum hydroxide. Okay, so we've got aluminum, oxygen, and hydrogen. And there's 1 aluminum. The 3 outside the parentheses multiplies 3 oxygens and 3 hydrogens. Then use the periodic table to find their mass. Aluminum, right here, we'll use 27 as its mass. Oxygen will use 16. And hydrogen, again, we'll use 1. So aluminum, 27. Oxygen, 16. Hydrogen, 1. And then we'll multiply. 1 times 27. 48. 3. And when we add those together, 27 plus 48 plus 3, 78. 1 mole of aluminum hydroxide in the Gaviscon, 78 grams. Do the same calculation for the magnesium carbonate. list the elements: magnesium, carbon, oxygen. Count their atoms. Magnesium is 1, carbon is 1, oxygen is 3. Find their mass on the periodic table. Magnesium is 24, carbon 12, oxygen 16. So magnesium 24, carbon 12, oxygen 16. Multiply 24, 12, 48. Add them up. 24 plus 12 plus 48 equals 84. 84 grams. Now, we'll do two calculations. One calculation for the aluminum hydroxide. That's the one that we know, so that's going to be our X in the first calculation. And in the second calculation, it'll be magnesium carbonate. And why we're doing the calculation is to find out how much hydrochloric acid can be used up. So we need to know those coefficients. The aluminum hydroxide and the magnesium carbonate don't have numbers in front, so that means that there's one of those in the balanced reaction equation. Alright, let's set up the first one. We have 0.160 grams of aluminum hydroxide. That's our X. So everywhere you see X, it's going to be aluminum hydroxide. So 1 mole of aluminum hydroxide over the molar mass for aluminum hydroxide, which we calculated right here, 78 grams of aluminum hydroxide, times, now our Y substance. Why we're doing the problem is to find out hydrochloric acid. So everywhere you see Y, I'll write hydrochloric acid. And we have 3 moles of hydrochloric acid for this calculation. On the bottom, 1 mole of aluminum hydroxide. And then the last step, the molar mass of our Y substance, which we calculated already. We calculated that when we did the calculation earlier for the Tums, 36 grams. 36 grams of hydrochloric acid in 1 mole of hydrochloric acid. Now we'll do the math. Multiply the numbers on the top. So let's do that. 0.160 times 1 times 3 times 36. And I'll write that down. 17.28. And across the bottom is 78. So I'll divide by 78. And let's call that 0.22 grams of hydrochloric acid. So one of the ingredients that's in the Gaviscon, the aluminum hydroxide, will use up this much of the acid that's in your stomach. We'll do the same calculation now for the magnesium carbonate. There's a different amount of that one, 0.105 grams. And we'll use the molar mass that we calculated for that up here when we do that first step. So 1 mole of our X substance, which this time is magnesium carbonate, over its molar mass, 84. Oops. Almost wrote Ca. That's my M. I messed up while I was writing it. Sorry. And then the next step, on the top, moles of our Y substance, hydrochloric acid, which in this reaction is 2 moles, slightly different ratio, 2 moles of hydrochloric acid. And on the bottom, 1 mole of magnesium carbonate. Okay, and then the last step, the molar mass of our hydrochloric acid again, 36 grams. Hydrochloric acid is 1 mole hydrochloric acid. We'll do the math by multiplying across the top. 0.105 times 1 times 2 times 36, 7.56. And across the bottom, if you multiply those together, it's 84. So 7.56 divided by 84 is 0.09 grams of hydrochloric acid. Both of these are working together, so we'll add together their effect. Together, they both will use up 0.31 grams of hydrochloric acid. Now that's less than what we calculated for the Tums. So maybe this one isn't going to be as effective as Tums. But not all chemical reactions go as far as it looks like on paper. If the reaction is not complete, or if the amount of the materials aren't actually what they say they are in the tablets, then we might get a different result. So 1 Gaviscon uses that much hydrochloric acid. But again, in our analysis, we're not going to analyze an entire Gaviscon. 1 Gaviscon tablet is going to be dissolved in 100 milliliters of stomach acid, but we're only going to take 20 of those milliliters, so 1/5 of a Tums, or 1/5 of a Gaviscon will be present in the sample. So we'll divide that by 5, and we'll see how much should be used up in the sample that we're testing. 0.31 divided by 5, 0.062 grams of hydrochloric acid. So that's how much we expect to be used up by 1 Gaviscon tablet. Okay, I did a demonstration video showing how much of the potassium hydroxide it took to react with the acid that was left in a sample that had reacted with either the Tums or the Gaviscon. When I did the titration for Tums, it used 12 milliliters of potassium hydroxide. When I did the analysis for the Gaviscon, it took 18 milliliters of potassium hydroxide. It took more because there was more acid left behind, because the Gaviscon didn't use up as much acid as the Tums did. It took less potassium hydroxide to use up all of the remaining acid because the Tums had used up more of the acid, so there was less left to titrate. How many grams of potassium hydroxide were in those milliliters that I added? I don't know which version you're looking at, but there was a typo that I corrected right here. We'll multiply to find out how many grams there was of potassium hydroxide in both of those titrations. And then we'll use that to figure out how much acid remained in each of the samples. So in our analysis, the thing that we're trying to find out is how much hydrochloric acid was left in the stomach juice. So that's why we're doing the problem. But what we know is how much potassium hydroxide it took to do the titration. So I'll use these numbers to start my these numbers here to start my calculation, the grams of potassium hydroxide. So for Tums, it took 0.12 grams of potassium hydroxide. And I'm going to multiply by 1 mole of potassium hydroxide, and here's its molar mass. So I'll put that on the bottom, 56 grams of potassium hydroxide. And then I'll multiply by, the Y substance is hydrochloric acid, and in our balanced reaction equation there's 1 hydrochloric acid. And on the bottom, moles of our X substance, which is potassium hydroxide, there's 1 mole of potassium hydroxide. And then we'll multiply by the molar mass of hydrochloric acid, which we used in our previous calculations, 36 grams hydrochloric acid over 1 mole of hydrochloric acid. And do the math. Multiply across the top, 0.12 times 1 times 1 times 36 is 4.32. Multiplying across the bottom is 56. Divide the top by the bottom, and it's 0.077 grams of hydrochloric acid. So the potassium hydroxide reacted with whatever acid remained. This is how much acid remained after the Tums tablet reacted with the stomach acid that was in the sample. So that's the result for the Tums. We'll do the same calculation for the Gaviscon. It's done using the same steps because we're trying to find the same thing. But we'll start with the grams of potassium hydroxide used in that analysis. So 0.18 grams of potassium hydroxide over 1 mole of potassium hydroxide and its molar mass times, on the top, it's potassium hydroxide, hydrochloric acid, the thing that we're trying to find out about. So 1 mole hydrochloric acid. On the bottom, 1 mole of potassium hydroxide. And then finally, 36 grams of hydrochloric acid. The Y, the thing we're trying to find out, why we're doing the problem, is to find out how much hydrochloric acid was left. And we'll do the math. Multiply across the top. 0.18 times 1 times 1 times 36 is 6.48 divided by 56 is 0.116 grams of hydrochloric acid. So that's how much acid remained out of the hydrochloric acid that was originally in the stomach juice sample. Now let's start putting these calculations all together. Okay, this is how much hydrochloric acid was in the samples before the tablets were put in. 0.15 grams of acid. And what we did was we just calculated how much acid was left after the antacid tablets reacted with however much of this they could use up. And what we found was that for the Tums, the Tums only left behind 0.077 grams of acid. And the Gaviscon left behind 0.116 grams. So out of the 0.15 grams of acid that were in the sample to start, this is how much remained because the rest was used up. Of the 0.15 grams in the Gaviscon sample, this is how much remained out of the amount that was started with. And so how much was used up? Let's subtract to find out. So the 0.15 grams that was originally in there minus how much was left is 0.073. 0.073 grams. That's how much acid the Tums actually used up out of the acid that was in the sample to start with. We'll do the same calculation here. 0.15 grams of acid were in the sample to start. This is how much was left, 0.116. So it used up 0.034 grams. A lot less acid was used up by the Gaviscon compared to the Tums. We calculated how much was expected to be used up. We expected that the Tums would use up 0.072 grams, and we expected that the Gaviscon would use up 0.062 grams. We did that calculation at the beginning. So compare that. This is how much acid the Tums used up. That's how much we expected to use up. It used up just a teeny bit more than we expected. The Gaviscon did not use up as much as we expected. Let's calculate the percent effectiveness. How much acid was used up compared to how much we expected. So the actually used up amount for Tums was 0.073 grams compared to how much we predicted, 0.072 grams times 100 to make it a percent. Do the math. 0.073 divided by 0.072 times 100 It'll be a little bit more than 100%. 101%. You know, if you buy something, you want to get 100% of what you pay for. Here, we got a bonus 1% effectiveness out of our Tums. Let's check out the Gaviscon. So the Gaviscon, let's see, we actually used up 0.034 grams of acid. How much we expected was more, 0.062 grams. Times 100 to make it a percent. Let's see. I'm guessing it's going to be like around 50%. 0.034 divided by 0.062 times 100. 54.8%. Let's call that 55. 55% effectiveness. So if you pay for something, you don't want to get 50% of what you pay for. You want to get 100% of what you pay for. The Gaviscon is not giving us 100% effectiveness compared to what we expected. And remember how much each one of these things costs. We get 101% effectiveness from something that costs only 3 cents a tablet. And here, for Gaviscon, we're getting about half as much effectiveness for something that costs 12 cents a tablet. 4 times more cost, half of the effectiveness. So there must be more to the story here. Why does the Gaviscon cost more and deliver less acid relief? Magic bowl of ice cream has the answer to the question. You know, in ice cream, there's an added ingredient that you might be unaware of. It's called carrageenan. Carrageenan is a seaweed that grows on rocks along the rocky coast. You can find it in the Atlantic Ocean. You can just reach down into the water and grab it out. It's used to make the ice cream smooth and creamy. Make sure I don't get brain freeze here. Now, that's really good. Vanilla, my favorite. The reason why this one costs so much more is because of a similar ingredient. You can look this one up. If you look up online, how does Gaviscon work? Or look up this, alginate. Sounds like the word algae. There's a kind of algae product found in Gaviscon, and it has a special job. It does something that Tums can't do. So if you want to find out the answer for why Gaviscon costs 4 times more, but only does half of the acid relief as Tums, look up this word here, alginate, and find out what its role is in the way that Gaviscon works. And while you're looking that up, I'm just going to finish off this bowl of ice cream here. You want some? Yeah. Good stuff, guys.